Hey, welcome back. So there's been a lot of hype recently about the Monte Carlo tree search algorithm, which is a fairly old algorithm that's been around for a while. But the reason it's gaining a lot of excitement is because of the new O1 models from OpenAI. And it's rumored that Monte Carlo tree search, or some sort of search capability, is built into the test time compute paradigm. So today I'm going to show you how the Monte Carlo tree search works. And we're going to build a really simple Tic Tac Toe game with a traditional Monte Carlo tree search element. So before we get started on that, I just want to play maybe a little bit of tic-tac-toe with O1 preview. So we will say, let's play a game of tic-tac-toe. And this is feeling very war games like at the moment, but let's move on there. It's going to think there. It's going to ensure engagement. Now, you saw that sort of thought process where it's going to figure out what it needs to do, create a game outline, etc. That is where the thought process or the Monte Carlo tree search element of O1 preview is meant to be. So let's play the game there. It's generated me a game board. So I'm just going to go in position 1 because I'm X. It's going to take quite a bit of time to come back with an answer. And then hopefully it should play its answer as well. So you can see here it's going to determine the move, it's going to clarify user intent. It's taking about 10 seconds to come back with that. And then it thinks quite sensibly that it really wants to be in position 5 in the center of the board. And that's actually a really good sort of position there. So let's pick, we will pick position 7. Let's see how it does. And again, it's going to think for a little bit of time here, and it's going to map out the game. And this thinking process, see, it sets up the game, mapping out the game, mapping the processing, and then it's going to try and work out its next move, and it's going to map out potential moves, and it's analyzing winning positions, and then eventually it's going to come back with an answer. And it's taken 19 seconds, so it's really thinking about this. And then it's came back and it's going to go for a 0. And that's actually a really clever move because it's blocking me off here, but it's also trying to create a winning position. So I'm going to fail the game for whatever reason. I'm going to pick number 2, and then hopefully it should recognize the win condition and be able to win the game. Now, if that works fine, we will then show you a non-large language model of how Monte Carlo tree search works with a kind of more traditional AI. And there you go. You can see it's kind of won the game there. So that's kind of what's going on. But this whole thinking element where it's actually formulating its strategy, working out what it's going to do, chain of thought, that analyzation there, that is where the Monte Carlo tree search element occurs. And by the way, you can download the code for what I'm about to show from my repository, which is Chris Hay UK, MCTS -play. So we will just open up my terminal for a second and we will play the game this side. So I have got a game here called Play Tic Tac Toe Game. So we're just going to type in Python tic-tac-toe-game.py. And you see it's going to render me a board here. So it's very similar to before. So I'm going to pick 1 here. And you see the computers came back and it's played position 7. This time I am going to press 3. And you can see it's blocked my move there. And then if I wanted to win the game, I could go and pick for 9 here. But I'm not going to do that. I'm going to potentially try and mess over the game here. So I'm going to pick 6 here. It's not made a great move there. Maybe I'll pick number 4 here so that I lose, and then you can see player O wins. And at the heart of this, we have an AI player which is built with a Monte Carlo tree search. I would argue the version that you saw with ChatGPT there was on the O1 model was a lot more powerful than the version that I'm showing you there. But that is fine because I've not given it a lot of iterations to think about this. So we're going to say no to play game, and I'm going to show you how we can build this. I'm going to open up our game here for a second. Now, I've created a thing called Tic Tac Toe Game 2. Tic Tac Toe Game 2, I will leave that in the repo. It doesn't contain the AI elements. It just sort of contains a player-to-player board. So you can kind of see here, I've got a thing called Tic-Tac-Toe Game Utilities, which allows you to print the board and check the winner. So if I go into there, Tic-Tac-Toe Game Utilities, you can see it's got defining winning combinations, and it just says this is the winning combinations for rows, columns, diagonals. This function here checks for a winner, and this function here checks to allows you to print a board. Again, here is a player move, so it's going to prompt you. So remember on the board it was saying enter your move, press 1 to 9. That's the piece that does this. It's just a little while loop, which allows you to enter in a move. It does a quick check to see if the move is valid, and then it returns the kind of state of the board. Nothing too exciting here. This is just sort of taking a turn, so it allows you to switch turns between each player, checks for the winner, checks for a draw, or whether the game continues. And then this is my main game loop where it initializes the game state, and then player X's turn, and then player O's turn. So in this case, I've not incorporated the AI at this point. This would just be player to player. So if I come back into my terminal for a second, and then we run the game one more time, but this time I do game 2. Now if I press 1, essentially I'm playing against myself, so we'll do 2. And then I'll probably do better against myself. I'm not going to block myself. I'll put 3. And then finally, I'll put number 4, and then I win the game and we won't play again. If we want to look at how Monte Carlo tree search works for a second, think of it as this ever-expanding tree of actions. So there's 4 phases within Monte Carlo tree search. The first one is selection, and that's really about choosing the most promising path through the tree. And then the next thing is expansion, which is really expanding all the nodes out of the tree. And then the other one is evaluation, so being able to evaluate your action and work out what the next state is going to be. And then the last one is going to be back propagation, which is really going back up the tree and updating the rewards of all of the nodes so that you can figure out the best path. So if we look at the selection phase for a second here, you're going to start with a start node, and then you have a list of moves that you can perform. So if we think of the Tic Tac Toe game, we're going to start with an empty board. And then as player X, I'm going to select my move. So in this case, the tree nodes are going to be whatever action or move that I'm going to make. So in Tic Tac Toe at this point, I would have 9 potential moves that I could make. Now, as I go through the chain, so if I go from move 1 and then I go down again into sort of move 2, then the number of available actions to me will reduce because player O is going to go, and therefore rather than having 9 potential moves, I'm going to move down to having 7 potential moves. So it's this kind of tree-like structure. So if we look at this diagram here, as we move through all the states, move 1B, and then I'm going to expand out from move 1B, that's the node that I've selected. Then the next set of moves, you've got move 2, move 2C, etc. We're going to expand out those nodes and then follow the path. So that's really the first one. So selection phase is the first part where we start at a node in the tree. And then what we're going to do is we're going to find the best possible child based on the policy. Now, if you don't know anything, it may be a random policy, but in the case of Monte Carlo tree search, you typically pick the child that has got the best possible reward model. So i.e. it's got the best score. So once I've selected my action, so in this case, I've maybe select my first move, then I'm going to, in the expansion phase, I'm going to generate all possible actions that I can make from that point. So it will be probably a subset of moves, and then I will go through, evaluate them. And in this case, in the expansion phase, you can see I'm just going to generate more child nodes after I perform each action, and I'm just going to expand out the tree going there. Once we've expanded out the possible nodes, we need to evaluate this, and that's what we're going to do by having an evaluation function. And then essentially we will get a reward for the model. So how good was that action? Does it result in a winning move? Does it result in a losing move? And then eventually I'll get a reward score, and then I'm going to walk back up the tree. So if I was at move 3A, and let's say that was a winning move, then I'm going to go up to the reward action of move 2, and then I'm going to update its reward because move 2 leads to a winning move on move 3. So if I'm at move, then I'm going to go up to move 1, and then I'm going to move up to the start. So if 3A is resulting in a winning move, then the path of 1B, 2C, etc. will have higher scores because we're leading down into this winning move, and that's why the reward model gets better. And then eventually, if we do enough iterations, we've visited enough nodes and we've expanded out enough stuff and done enough evaluations, eventually we will have the paths updated, and the paths with the highest scores are going to result in the best models. Now, That means the good things is that it's not extensive. You don't necessarily need to cover absolutely every single state because, if you've got a good reward model, when you evaluate a node, then that means that you, in the selection at the beginning, you don't necessarily need to follow paths that have got low selection criteria. So it leads you towards the best path. So eventually, once you've done all your iterations and you've got the score as good as you possibly can, i.e. the thinking time, then you're going to choose the node, the paths as each one that leads to the best possible score. And you just follow that as you perform each action. So that is essentially how Monte Carlo tree search works. So what we are now going to do is we're going to create ourselves an AI player so that we can try and repeat the demo that I showed 2 seconds ago. So if we have a look at the code that I created for a second, hopefully you're going to start to see in this code that all of this fits with the explanation that we just said a second ago. So you can see here I've got MCTS node and I've got MCTS search. And then eventually I've got 2 AI utilities, and then I don't remember what I said about iteration, so I've just sort of hard-coded that to 500 iterations, so it's going to do this 500 times. But you can kind of see here in AI move, the first thing that I'm going to do is create a root node for MCTS with the current game board state. So in this case, I create a node, I pass in the state. The state is coming from my AI move, and then I'm going to pass through an action function. And in this case, the action function is going to be suggest tic-tac-toe actions. So remember what we said when we looked at the Monte Carlo tree search. We're going to start at a particular node, and it could be, let's say, the start node, and we're going to generate all the possible actions that we could have. So in the case of tic-tac-toe, it could be 1 to 9. Or if I'm a little further down the game board, so let's say I'm at move 1, then there's going to be a smaller set of moves. And therefore, we're going to create a node for each possible node. That is where the action function comes in. So if I come back into Visual Studio Code for a second, you will see here that I'm going to create this node. I'm going to pass in the game state. The game state is going to be coming in from my game loop here. So remember this state here where I've got the initial game state, which is just going to be empty boards for the first game. And then I'm going to take a turn. In this case, it's player move, but we're going to move this to AI move in a second. Now, if we come in here, an AI move, it's going to call this suggest tic-tac-toe actions. And then if we look and suggest tic-tac-toe actions, all that is going to do is check who the current player is, and then it's going to return all the possible actions. So it's literally going to go through the game state board, and then it's going to tell you based on which cells are blank at that moment, because if you think about it, if it's not blank, it's going to have an X or a no, but based on the ones that are blank, it's just going to return back all the blank cells in that sense, and that will give us the possible actions. So if we go to our MCTS node for a second, again, this will represent any node within the tree, and it is literally just a tree structure. So at the top here, we've got node. Every node is going to have a state, and it's going to have a pointer back to its parent. Because if I'm deep down in the tree, so let's say I'm on move 9, for example, and I want to back prop up the nodes to be able to update their reward function to tell it the best possible path, then I need a pointer back to its parent node, and that gives me my hierarchical tree. It also has pointers to the children. So children, of course, remember, are the actions that you could possibly take. And then it's also going to keep a counter of the number of visits, how many times you visit a node. And then eventually it's going to tell you the reward function there. So that's going to be the score. So if you've got a good score, when you do the evaluation, i.e. you've got a winning move or whatever, then that number is going to go up here. And then here we're just setting what the action function is, so i.e. what's going to generate the actions from the state. And again, this is what we are passing in here. Remember, suggest tic-tac-toe actions. And then we're also going to pass in our evaluation function. And the evaluation function, in this case, if we come back into our AI utilities, in this case, it evaluates whether you have a winning mode here. So you see here, this is essentially your reward function. So I have a very simple reward function here. So if the move that you make results in you winning, so you see check winner, then it gives you a reward function of 1. If the opponent will end up with a winning combination, then you get a loss function of -1. And then if it's a draw, is 0.5. So i.e., if you follow the actions down and you win, you're going to get a 1. And then when we backprop the reward functions, the parents will have slightly higher to get down to the 9. This is where I said this is highly, highly simplified. Because if we were playing a proper tic-tac-toe strategy, then you would expect blocking an opponent would give you a higher score, or if you got the kind of, where you got in a kind of winning combination mode, so you win whether you got a vertical or a diagonal or a horizontal at the same time. So if you can make 2 moves at once, that would be the area where you would have a different reward function. So this is a really simplified reward function just to kind of prove it. That's why I'm saying, remember when we did it with O1, I'd said it had probably a more powerful reward function because it's probably learned those elements of strategy. Whereas my strategy at this point is really simple. If you win the game, you get a point. If you lose the game, you get -1 point, and then if you draw, it's 0.5, and then neutral is ongoing. But you can kind of see then the backprop, so the final action that you win, you might get 1 point, but then when we backprop back up the nodes, then rather than it necessarily being an O for an action, because it's a neutral score, you're going to get a slightly higher weighting, because we're going to average that. I'll show you that in a second, and therefore it would lead you down to that kind of winning score. So now that I've set my action function and my evaluation function, you can imagine that because this is a tree, you can have some things like has children, tells you if the node has any children, so it just returns self.children is greater than 0. And then the node has certain things that is required to satisfy what the Monte Carlo tree search is going to need. So we have an expand function. What the expand function does here is it checks if we have an action function. That's the first thing. And then if it does have an action function in this case, then it's going to generate all the possible child states. So it's going to pass in your state, the game board, and then it's going to basically churn out all the possible child states. So remember what I said before. So if we were playing tic-tac-toe, and in fact, we can just do that for a second. We are going to be on move 1 at this point, and therefore that move there is not available. So the only available moves would be 2, 3, 4, 5, 6, 7, 8, and 9. So it's going to pass in this state. The game state is going to be all of the states of each one of the cells of the board. And then obviously the evaluation function is going to return what actions are available. So in the expansion, the available actions are going to give us 8 available moves in this case. And that is really what's going on here. Once I've generated these nodes, 1 node for each action, then what we're going to do is we're going to loop through each one of those child states, and then we're effectively going to create a node for each one of those actions. And that is how we end up with that tree. Once we've done that, we're then going to check if we've got an evaluation function. If we have got an evaluation function, we're going to call the evaluation function. Remember, the evaluation function is my really stupid 1 minus 1 0.5 reward function. And then essentially we're going to set the reward value, which was 0, to whatever the result of that evaluation function is. So at this stage, if the game is ongoing, it will be 0. If we lose, it's going to become a -1. But if it's a winning move, it's going to become a 1. Or if it draws the game, it's going to be 0.5. So that node will now have a reward. And then as you can imagine there, as I visit all the various possible actions within the Monte Carlo tree search, these reward functions are going to be updated. And then eventually we're going to add the node to the tree. So I've also put in an optional early stopping. So if the maximum reward is achieved, i.e. I win the game, then it's going to stop expanding out and return the children. So that is essentially the expansion phase. Now I've got 2 other functions that are important here. One is called best child. Best child accepts in a policy function. And basically all it's going to do is when I am on a node, so let's say I'm on, I've selected an action of some sort, I'm going to check to see if there's any children. If there are children underneath that, I'm going to look at what the best child for that is going to be. So this is kind of helper selection policy. And then I'm going to apply a thing called a policy function. A policy function is essentially, when we look at the tree search itself, I'll show you what that is, but essentially we apply a policy function over the children, and the policy function will tell us what is the best child. Now, in this case, I have two policy functions created. One is a random policy, which basically looks across all the children of the node, i.e. all the actions, and then it just picks a random one. That's probably not a great policy because it's not going to get you to a win. As you can imagine, in this case, the best policy is going to pick the child with the highest average reward. So what that means is here's my reward. Remember what I said about visits. So it's going to accumulate the number of times that you visited and how many times it's got a reward function. And then it's going to average all of that out and then give you the maximum value. So that, so if you've got a nice high reward function, i.e. you're winning lots, but other moves have zeros or they have -1 that lead to lose, then that best child is going to pick the winning combination there. Or even if there's no winning combination and it's just a draw, it's going to pick the draw case there. And then finally on the tree, we have back propagation. Back propagation is what I said, it goes back up the tree. So if I've got a win, when I get that win, I am going to go up to the parent and then I'm going to back propagate all the way up and update the reward function there to give it a slightly higher value so that you know that you've got a winning path down the tree. So in this case, as I back propagate, I'm going to increment the number of visits to that node. I'm going to calculate the new average reward, reward minus divided by a visit. So I'm just averaging it out. And then I'm going to check if the node I'm on has a parent. If it does have a parent, I'm going to recurse. I'm just going to call propagate again. And then I'm going to visit the parent node. So in this case, here, if I'm down here at move 3A and that's a win, it's going to move up to move 2C, and then it's going to just apply the reward function in here because we won here, and then it's going to do the same to 1B. So if this has got a win and there's no wins over here, then these reward functions will be slightly higher than the other actions around that. And then it's going to drive you down to that win. Of course, if one of these other moves has a win there, that's going to be higher. And therefore, when I'm in selection, I'm going to end up picking the higher selected move because that's going to lead me to a win. If we then come back into our AI move, so I'm starting with the root node where I'm passing in the state of the game, and then I'm passing in my action function. The next thing that I'm going to do is I'm going to perform an MCTS search. So I'm going to perform a search. I'm going to pass in this root node. I'm going to pass in my evaluation function here. And I'm going to pass in how many iterations I want it to do, i.e. how many nodes. Now, the more iterations that we do, the more of the tree that we're going to explore, the longer it takes, but the more that we explore, and therefore the better answer we're going to get. If I only maybe have one iteration, I'm not going to necessarily explore all of the nodes. If I've got like 500 iterations or 10,000 iterations, then I'm more likely to visit all of the nodes, and therefore I'm going to get a better result. And if you think about that for a second, that relates exactly to how O1 is doing its thinking, right? So the more time it takes to think, essentially the more nodes that it's visiting. And again, it gives you the idea how that works. And then eventually it's going to call return the best move state. Let's just look at the MCTS search for a second. This is going to feel really familiar here. All that we are doing here is I'm going to set my selection policy that's passed through. In this case, I'm defaulting to best policy. And then I'm going to do X number of iterations. So I'm just going to loop around. And then I'm going to start with my selection node. So whatever action that I want to start with there. And then I'm going to do a win check just to see if we've got a winning. And then here, I'm going to move into the selection phase. So I'm going to check if there's any children. If it's got children, it's got children, I'm going to find the best child. I'm going to use my policy function, my selection one, to find the best child at this point. And then I'm going to see if I've got a node. If I do have a node, and that node doesn't have any children, I have not expanded it out, then I'm going to expand out the node. So I'm just literally walking through and I'm going to find my next best actions. If I've got children, I'm going to get the node. I'm going to maybe start with a random policy because I've just created the node in the first place. And now once I've got my child here, my possible action, I'm now just going to do simulation and back propagation. So I'm going to evaluate that state. And if that works, I'm going to back propagate back up. And I'm just at this point going to loop around, basically selecting the best value, doing 500 iterations, 5,000 iterations, how many. I'm just going to loop around, expand out where I haven't got nodes. So this is kind of the exploration phase here. But of course, I'm always going to start from my best possible starting point. So if I've got a really strong node, I'm going to follow that down. But I'm going to expand out these nodes. I'm going to find the best value there, make sure I've got coverage of every action. And then I'm going to perform the simulation, i.e. I'm going to evaluate the node, see if I win the game or not. If I win the game, then I'm good. And then if I do win the game, I'm going to back proc up the answers there. Eventually, after I've done all the iterations and visited as many trees as possible, I'm just going to select the best possible child of the root node. So wherever I started from, maybe I started at action at item 1, or maybe I started on move 7. That's where I'm going to start. And then I'm going to pick my best possible route towards a win. And then I'm going to say, this is the action that I want to perform. And then we perform that. And that is essentially how that works. And now, of course, if I want to be able to update my game, I just need to, in Tic Tac Toe Game 2 here, rather than making a player move, I'm just going to update that. And I'm going to say AI move. I'm going to click quick fix. It's going to move up to here. AI move is now part of this. And that goes to MCTS AI and then performs exactly what we just walked through here. And now we'll play the game here. And I'm going to press 1. And you see it's opted for 0 here. Now, this is why I'm saying if I want this to come back with better values, that's where I would spend time on either increasing the number of iterations, i.e. better coverage of the board, or I would give it a better reward function so it can pick up these other values. And then if I pick let's say I'm going to pick number 3 here, it's already recognized that it's going to lose here and it's actually doing the block. So it's figured out that blocking move from that reward function. And again, all it's doing is going through these actions and states and playing the game over and over. And then if let's say I pick, we'll pick number 4 because I want to do a terrible job. It's trying to go for the win here. So it's gone 0, 0, and then it's going to go for that here. I won't block it. I'll give it a chance to win here. I'm going to press 9, and then it's gone for the win. So pretty good here. But again, it's not the most perfect system because, as I said before, it doesn't recognize those kind of cross-tree things at the moment, and I'll prove that for a second. So if I go for 1, you see it's gone down there at the moment. So if I pick 3, it's blocked my win here. But now if I go down to move 9 there for a second, it can block me here, but it's not blocking me on number 6 and I win the game. So that's why I'm saying that although I've implemented the Monte Carlo tree search, really it needs a better reward function and it needs more iterations to be better at the game. Now, if I come back to ChatGPT for a second, maybe rather than playing 01 preview, which did a really good job there, if I play GPT 4.0, you'll see that it will do probably quite a terrible job. So we'll say, let's play a game of Tic Tac Toe. So similar to before, I'm going to press 1. It's gone with position 5. That's pretty good. I'm going to go with maybe position 7. And again, you can kind of see the terribleness of the situation. So it's went over here. 01 preview didn't make that move because it's thinking there. So it's just kind of making this next token prediction here. It's done a terrible job. And then if I press 4, I'm going to win the game here. You see the major difference between GPT 4.0 and 01 preview. It's not even a competition. 01 preview was blocking my moves. It was making good center blocks, etc. It was doing an incredible job, if you remember. In fact, we can go to the original game there. So if we come back here, you'll see. So when I place my position down in 7, like I did here, you see this made a really beautiful move in 01 preview. It blocked my X here, but it set itself up for a win here on position 6 if I wasn't going to block that. And if we just compare that to the exact same move on GPT-4o, you can see rather than doing the block at position 4, it put itself up onto the top right hand corner. Whereas this was the beautiful move here because it blocks me and it sets itself up for a win. Now, if we want to, we could also try this against O1 Preview Mini. And what you'll find is O1 Mini is not as good as O1 Preview. So let's do this again. Let's play a game of Tic Tac Toe. And we're going to play the game there. And it says, sure, let's play the game. So I'm going to go position 1 one more time. It's going to go and do its thinking. So it is thinking there, but you can see it's a lot faster than O1 Preview because it's a smaller model. It's going for the center, which is cool. I'm going to go for position 7 one more time. It's thinking about that. And you see piecing strategy, setting up game, exploring moves, evaluating strategic moves, thought for 7 seconds there. And again, ultimately, it's made the same sort of dumb move that O1 Preview wouldn't have made there. So it's closer to kind of GPT-4o in that sense. And then we know that I'm going to win in this particular case. So hopefully you get the idea there is Monte Carlo tree search is really a key thing. I think nobody knows. We don't know if it's being used with test time compute, right, with O1 models, but you kind of saw how the Monte Carlo tree search worked with a traditional AI. You can kind of see this for the thinking. It's following a kind of thought process, piecing together a strategy, weighing moves. It's kind of walking through the nodes, exploring move 3 for 0, evaluating strategic moves, etc. It's following a plan, and the chances are the plan that it's following is going to be doing this kind of Monte Carlo tree search piece. I think, if I'm honest, when we're looking at kind of the original O1 Preview and we're looking at the kind of summarized chain of thought processes there, and I'm picking that move where it thought for 19 seconds, it really is doing this step by step, setting up the game, mapping out the game, mapping out the process. I'm outlining the steps, updating the board, checking for wins, making my move, ensuring accuracy. Choosing the next move, I place X at position 7, updating the board. Now I must carefully select where O should go. I'm piecing together the user's potential winning moves, right? I'm looking at the rows, columns, and diagonals. I'm now analyzing the winning patterns, evaluating potential moves to create precedent. Okay, let me see. The assistant decides to block the user's potential. Do you see what's going on? It's the same sort of technique in Monte Carlo. It's doing analysis one by one, and then eventually it's going to make its final position there. So I think it's probably a fair bet that Monte Carlo tree search is being used at test time compute. But now hopefully you understand how Monte Carlo tree search works, and you will be able to implement that for yourself, and then you can explore for yourself how that gets worked with large language models. Anyway, I hope this video has been useful, and I hope you understand a little bit more about Monte Carlo tree search and how it works with the O1 models, potentially. Thanks.